Swayam Prabha. Digital India. Educated India.
Then we go for actuator selection. To discuss actuator selection, typically like we have these different choices available. You look at different options available and then make a choice based on that. Now when we have a positioning requirement, then BLDC motors typically are not used. Okay, we'll use permanent magnet DC motors, or you have also stepper motors here. Okay, so but we are talking of a servo. So in servo, stepper motors are not a servo kind of a drive. They are more like a open loop kind of a drive. Okay, so but depending upon application, you may do the choice. Actually, here we are required to do like servo operation by using some closed loop feedback. That's why we are kind of constrained to kind of using permanent magnet DC motors. That is a choice that we'll typically carry out. And then now the question is, how do you get power and torque for this motor? Okay, and then for this again, one can see that if we estimate now the mass in the system and forces that are coming, then we'll be able to kind of get to the torque. Now how do you get the forces? What are the forces can you think about for this linear stage motion? Okay, when we want to move it by say 20 mm per second kind of a speed. See, this is not very so we can say, okay, friction force, of course that is there, but how do you get to know what is force coming because of the inertia or moving elements or moving masses in the system? This is little kind of a tricky to estimate. Okay, so for that you need to know what is acceleration, which we have not specified in the problem. Okay, so we have specified, okay, I want to kind of go over the range of 60 mm, and then so that's where we need to get estimates of acceleration. Okay, so I'll tell you how do you get the estimates of acceleration. And once you have an estimate of acceleration, then acceleration is equal to mass into mass into acceleration will be the force, and that force times velocity will lead you to the power in the system. Okay, so there are this friction is what one element in the system that will affect the power, and inertia is another element that will affect the power. Okay, so friction estimation, you should have some kind of a ballpark figure estimates of the friction, and that for that you can use the tables online. You'll find some information about coefficient of friction between the two surfaces in presence of some lubrication or not lubrication. All those kind of things we'll make use of that. See what are the normal reactions typically from your applications coming on the system, and then you can estimate mu times n, friction force and friction torque. So many times this friction is much higher consideration than inertia, especially for the slow moving systems, slow motion systems, and systems which are having this kind of a spring loaded stuff. So as to enhance accuracy, one has to so you can see that this enhancement in accuracy or backlash consideration that comes at a cost of paying what cost you pay is extra power that you have to get into system to overcome this additional friction that will happen because of the spring loading of two elements. So this is an important thing now to you need to kind of plan a trajectory for getting this estimation of power. So we are on this question, how do you estimate power? And as I said, given the speed of 20 mm, range of 60 mm, 20 mm per second for the range of 60 mm, we have to assume something now to kind of get to the acceleration. Okay, we are not given directly any acceleration in the system, So how do you do that? Okay, we say, okay, we need to go from start to end in say 4 seconds, or this is one can we can ask the application user, okay, what is like, how much roughly the duration in which you would go for, like to go from one place to another place. Okay, so this is somewhat important. Say 20 per second, we go 60 like, but we don't know how soon we should get to 20 okay. So we cannot directly jump from start to 20 we need to have some acceleration to go to 20 per second kind of a speed. Okay, so we go, let's say we go start to end from in 4 seconds, so you can kind of do some kind of estimation. See, this is taking 3 seconds to go from start to end with 20 per second speed. Okay, so we want to do this operation say roughly in 3 seconds with acceleration, or 4 seconds with acceleration. So one can kind of say, okay, that number will be not too far from these 3 seconds. Okay, so we can plan, we can make some kind of assumptions of this sort, and then plan our trajectory for velocity. Okay, so now if I want to go now, say let's say I've chosen this 4 seconds or some whatever seconds time I've chosen, and I want to kind of limit my maximum velocity to 20 per second. Then I can shape okay, what are these straight line rise, okay, that will give me the acceleration to go from 0 to 20 per second speed. Okay, how much should be this duration such that when I complete my task in 4 seconds with this deceleration also for the same time duration as the acceleration time duration, then I reach this 60 Okay, so one can make such kind of assumption and proceed for getting the acceleration. Once you have acceleration, one can get to the force is equal to mass into acceleration. Okay, that so that is the maximum acceleration, maximum force that your system will see. Although during the range of this 20 constant speed, there is no force other than the friction force that will be seen. Okay, though no inertia force will appear because you are now moving at constant speed. Okay, so these are the kind of sense of, or this kind of a feel of how one can one has to kind of think and get to the estimates of power. Okay, so this is the power which is corresponding to inertia, and then we can estimate the power corresponding to friction losses, and then we get the total power in the system. Okay, so this is a typical kind of a exercise one would do for any mechatronic system selection of sensors and actuators. So now let us see this with the example of 2R manipulator a little bit more, because there are some kind of a variations that will happen here based on because the kinematic relationships will be different. Okay, so we'll talk briefly about that, and then we'll close this chapter. Okay, so now this is a 2R manipulator that you have done modeling for. Okay, and if this is a problem that is given to you, that okay, we like to go from point say starting point PS to some end point PF along a straight line trajectory. Okay, that is what is our aim for this, some kind of a straight line I have to kind of go along. So how do I carry out planning of this trajectory and then get further estimates of the sensor resolution? So I'm given that I have to go by the straight line trajectory for some kind of assembly line operation, and or some kind of some operation. Okay, and I'm given that okay, while on the trajectory I can be off the trajectory by some delta amount. Okay, so that is what is given as a user specification, which needs to get translated into sensor specification eventually. Okay, so I want to go along this trajectory, and I cannot be off the trajectory more than some delta plus minus delta amount, and then how do I kind of go about getting the sensor and actuator specifications. Okay, so you assume some kind of a inertia for these elements and things like that. So this will be typically an iterative process to, like say if you are designing the manipulator itself, it will be quite a few parameters that are going to be unknown to begin with. And so you'll start off with assuming some kind of a ballpark figure values, or some kind of you keep them as a variables, and then you keep on kind of simulating and changing. So typically what you'll do is, for such a iterative process, is to create some kind of Excel sheets, in which you key in these some of these parameters as input to the input block of the Excel part, and then you estimate some outputs, and then you see those numbers, and based on the numbers you start modifying the inputs to kind of get to what specification that you would like to achieve further. So that is one of the ways one can do nicely. So you're making use of the Excel sheets to do this kind of a design calculations a little bit iteratively. And you might have seen in your normal mechanical design process also, those kind of Excel sheets nowadays are available from many vendors, or some of the manufacturers catalogs. Okay, so this is our job, okay, to estimate now, going from this to this now. So first thing we will do is we should so the crux of this all is, how do you plan the trajectory? Okay, so as we saw in the last example also, once we plan a trajectory, a lot of things will estimate and will get clear. So now how do you plan for such a trajectory? So now say let us assume that, okay, I want to go from this initial position to final position in some time t, okay, or in some, say, 5 seconds or something like that. Okay, then how do I kind of plan my trajectories? Okay, so can you think of what comes to your mind at this point? Just put it on the paper, and then let's move on. Okay, so for this kind of a trajectory, what is first I need to kind of get some equation for this straight line, right? So we'll get the equation of a line first, to say starting from point. So you know from your basics of geometry, you can write this equation, not a big problem. So if you are given x p as a position, then corresponding to that, if I want to be on this straight line, a yp position will be given by this equation. Okay, even first starting point and end point, I am having this kind of a relationship to go if I know xp, but I don't know xp, right? Is not sufficient, right? How do I plan now? What is a thing is to plan for xp now. Okay, then my yp plan will be coming out of this relationship. So I need to plan for how my trajectory for xp will evolve in time. So we may say, okay, so can you think about how do you plan for now xp variable? What should be desired xp variable, so that I go from this point to this point in, say, some time t, or 5 seconds, say, for example. In 5 seconds I want to go from this point to this point, and I know these coordinates and other stuff, so how do I plan for this kind of trajectory? So then I say, okay, from xp perspective, again from this x value here, xps value, to xpf value here, okay, now this will be x value here. I'll need to go in same 5 seconds. Okay, so if I know this, then I can plan for this x part alone to begin with, and y part will be estimated from this. Okay, so now I can do this. Okay, I can plan, say, some velocity, say b mm per second kind of a velocity I will achieve during my motion path, and then I go again a trapezoidal kind of a form of a velocity. Okay, so in say t is 5 seconds now, in 5 seconds I want to go via this kind of a profile of velocity, and I have under constraint that so I again assume that okay, this is a time t1, and then this is also like total time from here to here is t1, so that you are accelerating and decelerating in the same time. And with that I would estimate what is a displacement that would happen, and that displacement should match to my x motion, which is xps minus xpf. Okay, so that is total x motion that should happen. Okay, so I'll plan this velocity profile first, and then like I'll estimate okay what is the acceleration, or like what is the speed number I can choose to kind of achieve the final displacement. Okay, once I know this, I'll get y coordinate from the equation that I have seen in the previous slide. So is this again sufficient? No, you can see that okay, this is not yet sufficient, because I just know now my x desired and y desired values for this point P, but they need to get translated to this Q1 and Q2. Okay, so for that you need to recall your kinematic relationships. Okay, so you plan first your x desired value, y desired value, and now come to kinematic relationships to get Q1 and Q2 desired values. Okay, so this is how like you recall your so you recall that coordinates of CG of link 2 were this much, this, and now if you change this LC2 to L2, then like that becomes coordinates of point P. Okay, use this inverse of this relationship to get to the values of Q1 and Q2. Okay, so you see that typically these relationships are not linear. Okay, they have some kind of a non-linearity in them, and that will have some kind of implications. Okay, so for example, for given xp and yp, there will be two possibilities for Q1 and Q2 solutions. Okay, one is on this side, you can see, and other solution will be on the other side, like the link going like that and like coming like that. Okay, symmetrics about a straight line joining from the origin to the point P. Okay, the symmetric solution on the other side. Okay, so one has to consider like that part in doing the inverse computation, so that you don't suddenly kind of go for some of the positions on the other side and some positions on one side, and then you'll have trouble in executing that kind of a trajectory. Okay, so from xp and yp you get to Q1 and Q2 now as a planned trajectories, and once you have these planned trajectories available, one can see now if there is a delta change in the resolution of Q1 or Q2, how much will be the change or like deviation from the straight line that is going to happen. And now one can see it's not very difficult to see that if I go for the same straight line here or at some other point in the workspace, okay, these relationships are going to change. Okay, so there are like some more considerations that will happen on the way. So what are the now like resolutions on Q1 and Q2? So given this kind of a trajectory plan, so I want to go to final position PF within some accuracy, say 10 micron, 50 micron, whatever micron accuracy. Then correspondingly what is like Q1 and Q2 resolutions that I'll need to have. So those are the kind of questions that we'll need to think about. So we'll discuss a little bit more in our discussion part again, but these are the things one need to think about. See, given specifications on the resolution on Q1 and Q2, how do you kind of get to the deviation from the straight line path, or reverse kind of a problem? Okay, inverse problem. Okay, So based on that, one can take a call on, okay, what is the resolution that is required on the sensors. Okay, and then one can also see, okay, that if I choose this PS coordinate starting point at some different locations, okay, say it is more closer to the origin or this motor, okay, then the kind of variation I would get for Q1 and Q2 would be different than range of motion that we'll get for Q1 and Q2 will be different from if I start from some other point. So where to choose this starting point from, if you have a choice, okay, if you are given some kind of a choice for the starting point, where you'll choose it from, okay, those are kind of thinking that you'll need to do. And for that, it's not a very trivial thing. One has to kind of do some simulations and see the workspace of this manipulator, and see which are the good areas in the workspace to have this operation done. Typically, one of the considerations is that if you are very close to this straight line position, singular position, okay, that we have talked about, so when Q1 and Q2 are Q2 is 0, okay, so only Q1 is there, Q2 is 0, then this is a straight line path, okay. And suppose now if I choose point PS at the end of that path, I don't have I cannot draw the straight line very easily, okay. I have to get out of this singular position, and then maybe I'll be able to kind of move along the straight line which is inside the workspace, okay. So this notion of workspace of this motion of point P, okay, workspace is basically all the set of points P which can be reachable by whatever the link lengths that are given here, and for whatever angles for Q1 and Q2, considering that they can move total 360 degree possibility. So those are kind of considerations that one would need to give for sensor specifications, okay. And when you come to actuator sizing, we need to go back to this modeling part to some extent, if at all we want to get into you remember this model that we have derived for the to our manipulator. So from this plan of Q1 and Q2 trajectories, one can get to know this is, say suppose this is Q double dot and Q dot, all these things are desired values, then I can get directly the torque which is required to kind of achieve that. Okay, so that is based on only inertial torques. No friction is considered in this equation yet. So if it is in a vertical plane, this gravity component will be dominant, okay, and the inertia components, depending upon how fast we want to kind of go, the inertia components may be dominant. So both C and D are kind of inertial terms in the system. Okay, so I will substitute these desired trajectories in here to get estimate of the torque is one way of doing things. Or one can kind of say that in the similar manner that we have seen what is the maximum torque that is maximum acceleration that is coming into the system, and estimating more kind of a conservative forces estimations of the forces coming, okay. And see now these matrices or inertia terms are dependent upon Q in general. So where you will choose to move that starting point PS, you'll have lot of variations that can be possible in the terms of dq matrix, and correspondingly like your estimates of the inertial torques. So once you have estimated some kind of a torque here, you can kind of consider that so this is coming as a tau 1 and tau 2 torque in first motor and the second motor. Then so by substituting your desired trajectories, then you use that with the velocity to torque into velocity as a power estimation for the motor, and this torque will give you maximum torque along the trajectory where it is happening, and based on that you can add some factor of safety and you can add friction also to estimate, like, some kind of a torque for your motors in respective joints. Okay. So now one can, okay, so this is about sizing the actuator in the same kind of a fashion as we did for the case of, so all these actuator sizing considerations will need you to plan a trajectory. Okay, that is the bottom line here. Okay, you need to plan this trajectory to kind of get to this. So for example, here we had just said this Q1 and Q2 will be obtained based on this plan for XP to move along the straight line. Okay, this is a kind of a so you'll have similar kind of a diagram for Q1 and Q2 again. Okay, so yeah, so planning the trajectory is an important step in many mechatronic systems, I would say. Okay, for whatever kind of a motion that you would like to carry out, you'll need to have this kind of a motion plan to get the estimates of the specifications. Okay, so that is what is the bottom line. And now I would suggest, like, you think about this problem. Suppose you want to, like, draw a circle. Instead of just moving along a straight line, I would like to draw a circle here. Okay, and I have given some accuracy and some speed of drawing circle. Okay, so speed of 10 mm per second is what I have been given. So the end effector here should be moving along this circle, okay, by a speed of 10 mm per second. Okay, then in that case, how would you plan this trajectory is a question. Okay, so the circle equation, something will be given, then how do you kind of plan now the further thing? Okay, so you think about this issue that, okay, I want to move my velocity along the circle should be 10 mm per second. How can I plan such a kind of a trajectory? Okay, so think about, okay, so is this a right choice for the coordinate system for the planning or not? You can think about that. Okay, so I will stop here. We'll see if there are any, we'll take up this again if at all needs to be in the discussion class part. Okay, so this is how, like, you can have now make this kind of a concept generalized. So from these two examples, first we have seen like a linear stage, which is single degree of freedom kind of a case, and now this is 2-hour manipulator 2 degree of freedom case. This can be now generalized to n degree of freedom kind of a system to think about. So for that you'll need your equations of motion in place typically. Okay, otherwise you'll get too much into too conservative estimates might be happening. If you don't really do the modeling completely, then your estimates, you can still kind of give actuators which are now, they can function, but they are like maybe too far more than what is required. Okay, so I think we'll stop here.